Bismillahirrahmanirrahim. Assalamu alaikum. So in this session we will learn how to convert a given dynamical system x prime to be equal to ax, where a is uh, not in canonical form. So our task is to convert this a, transform this system in a form such that this matrix becomes canonical. So first we will assume that the case that we are going to discuss is case 1, let's say, and I would say that suppose we have a system, suppose A has two real and distinct eigenvalues lambda 1 and lambda 2 with v1 and v2 as corresponding eigenvectors. So we have a matrix A involving in this system where A has two distinct real eigenvalues lambda 1 and lambda 2, but the system is not in canonical form. So like now we will transform this system in a form where this matrix multiplied will be canonical form. So I'll start this way. So for this I will first define T, a matrix T, which has columns v1 and v2. Okay, or you can write it maybe T equal to v11 and maybe v11, v12, v21 and v22. So in this way this capital V1 will become equal to v11, v121, and this capital V2 will become v12 and v22. So now what I can do is I can apply this transformation into standard basis. First let's consider this E1 is basis. So E1 is what? Where 1 comma 0. So this is E1, the standard basis in R2. Let's apply T on this 1 0. So my T is v11, v12, v21, v22, and I'm applying it on to 1 0. So you can easily check out that this becomes v11 and v21, which is equal to v1. So this means that when I apply T on E1, it gives me v1. Similarly, now consider another basis, that is E2, and it is 0 1. Now I'll apply T on this 0 1. So v11, v12, v21, v22 operating onto 0 1, and it gives me v12 and v22, which is basically v2. So that means what? That means when I'm operating T onto E2, I am getting v2. Okay, so the bigger picture from this small discussion is when I operate T on E1, I get v1, and when I operate T on E2, I get v2. Similarly, from here I can also write T inverse v1 equal to E1 and T inverse v2 equal to E2. Okay, so now I want to define one particular transformation that we have discussed in the previous session too. So that is T inverse A T. Okay, and I want to find its matrix form. the matrix form of this transformation. And you know from linear algebra that whenever we are interested in finding out the matrix form of any transformation, we apply it onto basis. So in this case I'll apply this transformation into standard basis. First I'll operate this on T inverse AT on E1, and you can see that this is nothing but T inverse AT operating onto E1, and this is equal to V1 from here. So this is equal to T inverse A V1, but V1 is eigenvector of this A. So this T inverse, this is lambda 1 V1, but I can snatch out this lambda 1 over here, then this is T inverse V1, and but this T inverse V1 is E1, so this is lambda E1. Okay, so that's one relation. Now I'll similarly operate this onto E2, the same transformation. T inverse AT, I'll operate onto E2, and this can be written as T inverse ATE2, but we have seen that this is equal to V2, so this is T inverse A V2, but V2 is eigenvector of A, so this is nothing but T inverse lambda 2 V2. Then lambda is a scalar, so we get T inverse V2, and then lambda 2 times this is nothing but E2. Okay, so what we have so far, so we have these things. What we have is T inverse AT. When I operated onto E1, I got lambda 1 times E1 plus 0 times E2 in the previous part. Then T inverse AT, when was operated onto E2, we get 0 times E1 because E1 is not here, plus lambda 2 times E2. And now you know that when we convert it, when we write this into matrix form, so this gives me T inverse AT equal to, from linear algebra, this lambda 1 0 becomes first column and this will become second column. Aha, so what we have now, what we have done now, we have something interesting over here, this part, and this suggests that if A has distinct eigenvalues lambda 1 and lambda 2 with eigenvectors v1 and v2, then T inverse AT, where T is what you know, T is defined at v1 v2, then T inverse AT can be written as lambda 1 0 0 lambda 2. So when you have A with distinct eigenvalues, you just calculate its eigenvectors v1 and v2, and you will write this T, and then you will find its inverse, and then you will calculate this thing, this quantity, and this will give you the canonical form. And then you define this system, T inverse A T Y. So this means that if x prime to be equal to ax was not in canonical form, now we have got another system which is transformed version of this system, and this system is in canonical form. And now we can talk about this system's fixed points, and you know that this becomes canonical form, and we are very well aware about the canonical forms. So, and specifically this will become this form, like this will become nothing but lambda 1 0 0 lambda 2 times y prime, and if both the eigenvalues are less than 0, then it is going to be sinc, and if one is greater than 0 and other is less than 0, then it's going to be saddle, and if both are positive, then it's going to be source. So you can talk about them now very easily. And in fact, once you have solution to this system, because it is easy to calculate its solution, so once we have solution y of t, then just we will operate t on it, and we will also be having the solution of this. So in the next video we will be doing some example of it.